So this very exciting work that we're doing, especially using high resolution and high sensitivity observations to probe the organic or molecular inventory of planet formation. And I think this little cartoon that I have in the background really kind of nicely illustrates the different regions that we're trying to probe with these high resolution observations. So you see in the background here we have a star surrounded by a dusty swirling disk, and then we have this region on the outside which is white, it's shiny because the dust grains are coated in ice, and we state this boundary kind of between the rocky material and the outer icy material is the snow line in the protoplanetary disk around the young star. So I'll give you a little bit of an introduction into what we might have expected to have seen. I'll give you some highlights from some of the early results that we've had in this field, and then I'll go on to talk about much more recent results, in particular those of our recent large program that we have on ALMA, the Atacama Large Millimeter Array. So just to get started, so one of the big questions that we want to answer when we study these structures around young stars is to gain insight into our origin. So all of the physics and chemistry that happens even well before the stars form, such as in here in the molecular cloud in the interstellar medium within which young stars will be born. So our origins, where do we come from, what physics and chemistry is important, and then setting kind of the outcome of the star formation and planet formation process. So we have a lot of different kind of questions that we answer in this. For this audience in particular, I think that one of the questions that we have, especially in these structures that form, such as the protostellar disk, so an orbiting disk of dust and gas and ice, that surrounds a young star just after its birth, that's formed just through angular momentum conservation, and then onto this structure here, the protoplanetary disk, which is the disk that's revealed once the surrounding collapsing envelope from the forming star is dispersed. So these environments are really unique astrochemical laboratories. They will inherit to some degree the molecules and volatiles that have been formed in the molecular cloud, but their own unique physics and chemistry may also modify that material as well. And so this kind of trail that you see in the background is really thinking about that trail from the molecular cloud material through the protostellar disk into the protoplanetary disk, and then finally into the planets and other objects that we have in the solar system, such as comets. So of course, comets are also a very important source of information and are themselves very unique astrochemical laboratories as well. So we want to probe what's the origin or heritage of planet and comet building material, and that also feeds into our origins. So we like to think of chemistry as having a hierarchy. We start with simple molecules, we move up to more complex molecules, and then finally that creates our feedstock for our prebiotic chemistry, hopefully. So I'm going to focus mainly on the protoplanetary disk structure in this talk, and I'm just going to talk you through a few slides to describe what we expect the structure of these objects to be. So I call this the anatomy of a protoplanetary disk. So as I said just in that short introduction, these structures arise naturally when a molecular cloud collapses to form a star, and they arise through the conservation of angular momentum and the fact that the star needs to be fed material through a disk in order for it to accrete from its envelope. So they play a very important role. They aid accretion, they conserve angular momentum, but they're also the sites of where the planets and planetary system will form as well. So this is a little slice, if you like, through section, through an edge on protoplanetary disk. We have a star in the center. We have this midplane. This is the important region if we're forming planets. This is where we have the greatest density of material. In terms of their composition, they very much mimic what we have in the interstellar medium. They're 1% by mass, and then volatiles in the form of gas and ice are around 99% by mass. So a lot of the planet formation process story actually starts with the dust, but the dust is only 1% of the mass. If we're thinking about forming in particular gas giant planets like Jupiter or Saturn, then the volatiles will also play an important role in setting the composition of those atmospheres as well. So you can see here that we've, in this little cartoon, I've just shown you that we have gas and we have ice. And again, just highlighting this important region that we have in the midplane, which is the temperature boundary, because our temperature structure is such that we're mainly heated by the star. So the inner regions of the disk are warmer, and then they cool as you move outwards, as you increase the distance away from the star. So you'll reach some temperature boundary at which water ice will begin to condense on the surfaces of dust grains. And this is what we call the snow line or the ice line. But these disks are not geometrically thin objects. They have some vertical extent as well. And that's driven by heating from the central star that heats the gas, and the gas sits in hydrostatic equilibrium. So it's not just that you have this reservoir of ice sitting in the midplane, you also have an ice reservoir kind of in the upper regions of what we call the disk atmosphere as well. So we don't just have this water snowline concept, so this temperature boundary, where within this temperature boundary we have only rocky material available for planet formation, and outside of that we also have ices available for planet formation. As any of you that are astrochemists in the audience know, that different molecules that are fairly common in the interstellar medium have different volatilities. So as we move outwards in the disk midplane, we sequentially start to freeze out higher and higher volatile, or more and more volatile molecules. So for example, we'll have an equivalent snow line for CO2, beyond which CO2 will freeze out as ice on the dust grains, and then further out in the disk we start to freeze out even our hypervolatiles that have a very low desorption temperature, such as CO, and N2 would be another example of that. So why is this important? So again, if we're thinking about planet formation, and in particular gas giant planet formation as well, depending on whether you're assembling your planet and your planet's atmosphere in the disk relative to the positions of these snow lines, you're going to very drastically change the elemental composition of the gas, because these are fairly abundant molecules. So they're the main carriers of oxygen and carbon, for example. So if you freeze out oxygen, you start to remove oxygen from the gas phase, and that means that those atmospheres assembled, for example, between the water and CO2 snow lines would be more oxygen poor than those assembled from within the water snow line, for example. So the locations of these snow lines is quite an important property for us to try to map in protoplanetary disks. And if we have a sun-like star, then the positions of these snow lines lie about these different distances. So the water snow line is around 1 AU, the CO2 snow line maybe around a few AU, 5 AU. The CO snow line is typically much further out, again, because we need very cold temperatures in order to freeze out CO. So the CO snow line would lie a few tens of AU, for example, around in a disk around a sun-like star. So you can see here in this cartoon, we can't only think of disks having this radial structure, especially in the ices. They also have a radial structure in the ices and in the gas as well. So it's not just the locations of these snow lines that are important. As I'll come on to describe, when we're looking at molecular emission from disks, it's really these upper disk regions that we're probing. And then we also have these multiple snow surfaces that are also set by the relative volatility of molecules. So as the protoplanetary disk lives for between 1 to 10 million years or so, there's a lot of different physics that takes place that then influences the chemistry and the chemical structure. Aside from the heating from the star, another fundamental processes that take place are also what the dust is doing, as well as what the gas is doing. So we now know from kind of a couple of decades now of submillimeter observations in particular, but also scattered light observations as well, as I'll show you, is that the dust in disks is not homogeneously distributed through the gas. There's a lot of different dust physics that goes on, such as growth, so dust grains can collide and stick and grow. They can also fragment if their relative velocities are sufficiently high. That can replenish small dust grains that we can then see in scattered light. The dust grains in the outer disk in particular will start to decouple from the gas. So the gas feels its own pressure and actually orbits at slightly slower velocities relative to the dust if the dust is sufficiently large. So the dust is trying to orbit at Keplerian velocities, the gas is slightly sub-Keplerian. The dust feels a headwind, feels a drag force, and drifts inwards. And also the dust, once it's large enough, depending on where you are in the disk, it will also start to gravitationally settle towards the midplane as well. So despite globally the dust being 1% by mass, locally within the disk, we don't necessarily expect that that ratio to persist. Our dust grains will grow, they will change in their size distribution, and also the local gas to dust mass ratio will change as well. And this process of settling and drift, we're starting to see very clear evidence of that in high resolution observations of the dust thermal emission, as I'll show you. So we're starting to see very much a lot of these predicted effects in our disks, in our real life disks. So let's now take a little bit of a closer look at the chemical anatomy of a disk. So I already explained the concept of the snow lines, and I explained the concept of the snow surfaces. But when we point our telescopes at protoplanetary disks, then what we're really probing is this molecular layer. So this layer, which is not frozen out, part of it may be frozen out, but some molecules are in the gas phase. So we call this the molecular layer. And this is a layer that's usually moderately warm, so between 20 to 50, 60 Kelvin, where we have quite a rich gas phase chemistry. And that rich gas phase chemistry can be driven by ion molecule processes that are also triggered by penetration of radiation from the central star. And that radiation from the star can also ionize and atomize the upper layers as well. So this tends to be what we call the disk surface. So you not only have that chemistry driven by the central star and also the effects of freeze out leading to ices in the midplane, the disks themselves are also exposed to radiation from external sources. So our galactic cosmic rays, for example, would have sufficient energy to penetrate and perhaps even modify the ices. If you're in a region of enhanced UV, maybe you're nearby a young, O-type star or something, then that interstellar UV radiation can also affect the outer regions of the disk. So here I've already explained the concept of the snow lines, but again, if we point a telescope at a protoplanetary disk, and in particular from infrared to millimeter wavelengths, then what we're really probing is this molecular layer. So molecular emission coming from this molecular layer. And this has really been exploited very well by previous and existing instruments. So there's a lot of studies at near infrared wavelengths, really looking at this inner very hot region around protoplanetary disks within a few AU, really looking at the molecular disk atmosphere. In the mid-infrared, we had Spitzer, for example, did a lot of work in this region, looking at the molecular layer at a few hundreds of Kelvin in temperature, probing a region within about 10 AU. And of course, we'll have JWST will make a really big impact in the study of this region in particular in the near future. But most of the disk is actually very cold and is best probed at much longer wavelengths, so submillimeter to millimeter wavelengths, where we can actually exploit rotational spectroscopy that gives us a benefit, if you like, over infrared spectroscopy, in that the molecules themselves really have a unique a spectral fingerprint that really helps us to kind of increase the size and complexity of the molecules that we can detect. And those rotational transitions are excited just at the temperatures of the outer regions of the molecular layers of disks at a few tens of Kelvin. So this is really what I'm going to focus on today, is what we're learning from high resolution submillimeter or millimeter spectroscopy of disks. So I've just given a very short introduction into molecular spectroscopy, and in particular on rotational spectroscopy, which we exploit, if you like, in astrochemistry, to give a lot of insight into the physical conditions of the objects that we're interested in. So protoplanetary disks are mainly molecular in nature. They're reasonably cold objects, so most of the gas material is in the form of molecules. And we exploit molecular spectroscopy, in particular rotational spectroscopy, to give us a lot of derived properties of these objects, such as the gas mass and distribution, by looking at multiple line transitions, we can get temperature, excitation information. We can get information on gas density by looking at dense gas tracers, very much like is done in the interstellar medium. It directly gives us the composition. We know what molecules are there. And the ice composition indirectly as well, through, for example, we know that certain molecules are formed only on the ice, which is, or predominantly on the ice, such as water itself, but also molecules like methanol. With very high spectral resolution, we can get a lot of information on kinematics. I'll show you a little example of that. But other properties of the disk, such as turbulence, so one of the big questions is what's actually driving the accretion of material through these objects onto the star. And that's thought to be linked to the turbulence present in the disk. And if you're interested in the ionization structure, again, which can be very important for the kind of transport mechanisms, again, through the disk, through the coupling with, for example, magnetic fields, then measurement of the ionization fraction is very important. And we do that with small positively charged molecules like HCO+, for example, would be a powerful tracer there. So through molecular spectroscopy, exploiting that, we can actually gain a huge amount of information from these objects. So what do protoplanetary disks look like in terms of their molecular inventory? So what have we actually been able to detect in these objects? So this is a little spectrum of molecules. I don't expect you to read this in any detail. This is really just to give you an idea of what we have detected in space to date. So this is kind of the spectrum of molecules that we've detected in the interstellar medium and also in other very molecular and chemistry rich environments like in evolved stars, for example. And we go from everything from like small diatomic molecules, like very common molecules like H2, CO, for example, all the way up to kind of these large complex organics that are typically found in the warm, dense regions around forming stars, in particular around massive stars. And we also have some very exotic species that have been detected in space, such as molecular anions, and also these kind of very long chain hydrocarbons, unsaturated hydrocarbons. So for example, we have C8H here minus C8H minus, which is 8 carbon atoms with 1 hydrogen, that's also negatively charged as well. So interstellar circumstellar chemistry can make a wide range and a wide diversity of different molecules. So in terms of what we've detected in disks to date, this is kind of what we've been able to see so far. So you can see that we're not seeing the same level of complexity yet in disks. So we're reaching molecules up to 6 atoms in complexity. And if you look at what we're detecting, we see small diatomic, triatomic molecules. We see common cations like HCO+, N2H+. In the infrared, we've seen a lot of the kind of small stable infrared active molecules like water, CO, and also acetylene, ammonia, methane, for example. And mostly the molecules that we're seeing are quite stable molecules in the sense that we're not seeing, we're seeing quite a high degree of saturation, for example, but also the molecules themselves are quite stable. So, but you can see that we're starting to kind of get up towards the more complex molecules with rotational spectroscopy. So we have around 25 molecules out of the 200 plus or so. So of order 10% of detected molecules in space have also now been detected in protoplanetary disks. So this gives us a huge reservoir of information, again, exploiting those properties that we can extract from molecular line observations. So about, I think 10 years ago or so now, maybe slightly more than that, we had this machine here come online, which is the Atacama Large Millimeter submillimeter array. And this really gave us a big leap forward in our understanding of the submillimeter and millimeter emission from protoplanetary disks. And the reason for that is because if we take a typical protoplanetary disk, it's around 100 astronomical units in radius or diameter. The nearest star-forming regions are of the order of around 100 parsecs or so away. So that means that these objects are actually really small on the sky, so only a few arc seconds at most on the sky. So in order for us to really not only just detect molecular emission from these objects, if we wanted to actually really resolve it, and in particular get down into the planet forming region, which is within a few tens of AU rather than a few hundred AU, then we need interferometry, and we need interferometry that can be done at millimeter or sub-millimeter wavelengths. So because what we really want to see is that those cold regions of the protoplanetary disk. So the molecular region of the disk that's only a few tens of Kelvin in temperature. So about 10 years ago, we had this wonderful machine here, ALMA, finally come online. So ALMA is an array of radio, submillimeter, millimeter telescopes and radio antennae you can see there that operate between 30 and 900 gigahertz. So right within the frequency range that we need for rotational spectroscopy of most molecules, especially all those tracers that we have available to us in protoplanetary disks. So just to give you a little snapshot of what we're learning about the dust distribution or emission from dust in disks in this era of ALMA. So in this era of high resolution interferometry at millimeter wavelengths. So the first kind of key survey that I want to highlight, you may have seen this before, is the D-SHARP survey, which was a large program executed a couple of cycles ago and was the first large program dedicated to protoplanetary disks. And this program operated at about 1 millimeter and had very high resolution observations of the dust thermal emission from an array of 20 protoplanetary disks, all selected because they were otherwise well studied. So this is the array of D-SHARP results. So these are the 20 sources observed with D-SHARP. The resolution of these observations is a few AU. I think between 4 and 6 AU, it depends on the distance to the individual objects. And what these high resolution images show us is that the thermal emissions, what you're looking at is images of the thermal emission coming from the predominantly millimeter sized dust grains in the protoplanetary disk. And what these images show us is that the thermal emission has many different morphologies, but the most common of which are these kind of ring-like concentric, highly concentric ring-like structures. Some of the objects have spiral arms. So here's one here. Here's another one, IM lip, that I'll talk a little bit about. Some objects have very defined rings. Some objects have a little bit more kind of diffuse rings. Some objects also show hints of these kind of azimuthal asymmetries where there's kind of an increase in the thermal emission in certain locations that people think are pressure bumps where dust has been able to be trapped. So a huge diversity of structure when we kind of put our ALMA glasses on and look at the thermal emission from the disk. But one of the questions is, well, what are these structures telling us? What are we learning about these objects by seeing this very highly structured thermal emission? And one of the, well, I suppose the explanation is that if we take, I think this is AS209 up here, is that in this object, you have some mechanism that has created gas pressure maxima. That could be a planet, but there are other mechanisms as well, such as hydrodynamic instabilities. So they have created gas pressure bumps that have trapped that dust that's been trying to drift inwards through the radial drift phenomenon that I showed you about. And then the dust is getting trapped in those pressure maxima, so can no longer drift inwards. And then because of the trapping of the dust, you get this very defined thermal emission. There's alternative, I think for AS209, there have been models that show that likely this large outer gap up here are likely due to a gas gap formed by a forming planet, for example, because planets exert torques on their protoplanetary disk and do create quite deep gaps, which also create these pressure maxima. And certainly we know planets form in disks, so there's a prevailing, I suppose, theory in the community that some of this, if not all of this, is triggered by, in some sense, the planet formation process, these structures. So a high diversity of structures, no two disks look the same in the dust thermal emission. Planets are possibly the prevailing solution to why we see these substructures. I also want to highlight a nice more recent result by Villeneuve and collaborators, where they've been doing studies of edge-on protoplanetary disks. So what you see here is a color map, which is the scattered light, which has been done at shorter wavelengths, so near infrared wavelengths. And then in the contours, you're looking at the ALMA thermal emission again. And what you can see in some of these edge-on systems, so here's one here, IRAS 04302, it's another quite well-studied object. So you see the scattered light is coming from a scattering surface, which is quite far away from the location of the star. But the thermal emission from the millimeter grains is coming from very, very narrow region. So these grains are sitting in a very flat disk, despite the fact that the disk itself is quite flared, as is evidenced by the scattered light, which is kind of tracing where the small dust grains are and where the gas is. And you can see it again here in Herbig-Haro 30, very, very flat, Tau 042021, very, very flat. So the D-Sharp survey shows us this evidence of this drift of dust and trapping within pressure maxima, possibly triggered by planets. And what these edge-on studies are showing us is that this dust is really settled very, very close to the midplane. So we're seeing the evidence of those two effects that I described in the introduction. This settling towards the midplane, giving us a very flat dusty subdisk, if you like, again, where the planets will be forming, and then also this kind of evidence of trapping that's also driven by the radial drift phenomenon. So observations like this also give us a pretty good handle on the turbulence that's ongoing in the disk, because if the disks were particularly turbulent, then they would have some effect on the dust as well. So whether or not those large dust grains were able to be lifted or lofted back up into the atmosphere depends on the level of turbulence in the disks. This is very interesting for those of us interested in planet formation. So kind of the third kind of feature that we've been seeing is also spiral features in dust emission as well. So here's a nice object that's also, I'll come back to a couple of times. This is a scattered light image from SPHERE at near infrared wavelengths of this disk around IM loop. And then what you see on the right is the ALMA image. So this is the thermal emission and this is the scattered light emission. And you can see that you can see the top side of the disk, so the disk is inclined to our line of sight, and you're seeing this very high aspect ratio scattering surface. It's scattering the light back towards us. And you also see scattering from the lower part of the disk as well. So this looks to me a little bit like, I don't know if you remember like yo-yos, where you have the string, and then you wind the string, and then you have the yo-yo, which is kind of, or an Oreo cookie or something like that, but with a really high aspect ratio. So it's telling us that this disk is really flared. So it's got a very high scale height in the gas, because the gas is also traced by the scattered light to some extent. The ALMA image shows us these really intriguing spiral arm features, but these images are not actually at the same scale. So you can see the scale bar here at 1 arc second, another scale bar here at 1 arc second. So if I make that the right scale, you can see again that the thermal emission from the large grains is coming from a much more compact region than the scattered light. So again, evidence of this radial drift phenomenon. The pebble disk, where the millimeter grains are, is a lot smaller, more compact than the small grains traced in the scattered light. So a lot of really interesting dust morphologies and dust physics that we're starting to see with these high resolution images. So moving on a little bit more to the kind of topic of the talk, if you like, is the organic inventory of planet formation. And in particular, I want to first show you a few highlights from ALMA, and then move on to tell you some of the first results from a dedicated ALMA Large Program that we've been analysing the data for the past year. So I want to come back to this, first of all, this concept of snow lines. So this is our solar system. This is a little cartoon of what the dust and ice may have been doing in the solar system. And again, the snow line is this region here. So the region that delineates between the inner a rocky material that's devoid of ice versus that where the temperature is cold enough for ice to condense out onto the dust grain surfaces. And this is important for planet formation because we also think that this basically set the boundary between our inner terrestrial planet forming region and our outer gas and ice giant planet forming region. The idea being that the freeze out of ice gives you a bump up in solid material, gives you increased stickiness, if you like, for forming the cores of the giant planets. Now, the water snow line lies in a disk around a star-like sun at about 1 AU. So this is actually a really difficult region to get down to probe in other astrophysical disks. But the CO snow line is one of the snow lines that, again, we can probe with observations because it's sitting out at a few tens of AU, which is the resolution that we can now reach. And one of the nice early results from ALMA was the indirect measurement of the location of the CO snow line in two objects. So the one on the left here is TW Hydra. This is a very well studied object. It's the closest one to us. It's also almost face on, so we get a really nice view of the radial distribution of emission coming from TW Hydra. And then the second one here is IM-Loop again, so you've met IM-Loop a couple of times now. And this is a N2H plus emission, and this is DCO plus emission in the blue here. So the reason that these two images trace the location of the CO snow line is because of astrochemistry. So on the left-hand side, the reason that N2H plus lights up in this ring is because when CO comes freezes out onto dust grain surfaces, it's removed from the gas, and it's the main kind of destroyer, if you like, of N2H plus because it's got a higher proton affinity, so it steals away the proton to make HCO plus. So where you see N2H plus light up is where CO is being removed from the gas phase. And then DCO plus is the similar reasoning, but for the opposite reason, in that we need CO in the gas phase in order to form DCO plus. So you can see here in the dashed lines, I give roughly the locations of the CO snow line. So you can see N2H plus lights up outside the CO snow line in TW Hydra, whereas in IM-Loop, DCO plus lights up at the location of the CO snow line. IM-Loop is also interesting because it's got this outer CO snow line that we think is driven by external heating or external photons that are helping to release the CO back up off the gas phase. So this is a particularly large protoplanetary disk, so large that the external environment starts to affect its chemistry in the outer regions as well. So you saw those beautiful molecular rings of N2H plus and also DCO plus, but we see molecular rings actually, even in moderate resolution images, more or less everywhere. So here's another nice example. Again, this is TW Hydra, our closest protoplanetary disk, almost face on. This is now traced in C2H+, which is a radical species. And here's another object, DM Tau, in the Taurus star-forming region, and it's in the same molecule. So you can see here in TW Hydra, the emissions in this nice ring. In DM Tau, it's got this compact component, and then this other fainter ring in the outer disk. And if I just draw again on a line, so what these two dashed ellipses show you is actually the spatial extent of the continuum emission of millimeter wavelengths, or if you like, the spatial extent of the millimeter disk, so where the millimeter grains are. And it appears that this particular molecule lights up, it starts emitting quite strongly just outside of the pebble disk or of the millimeter disk. So there's something very interesting about the chemistry of C2H+ that is linked with the dust evolution in the disk. So remember, the dust is settling and drifting inwards. And what we're seeing is C2H starting to emit kind of beyond that boundary where the dust is emitting. So one of the theories for this is that why this hydrocarbon, but other hydrocarbons as well, are quite bright in the outer disk, is that it's tracing a CO-rich gas, or sorry, a carbon-rich gas with a C over rho ratio of 1 or even higher. And the reason for that is, again, coupled with this dust settling and drift phenomenon, those dust grains that we have in the outer disk are also coated in ices. So if the dust grains are growing, settling and drifting inwards, they're also bringing those ices that they host deeper into the disk and further in towards the star as well. So instead of that picture that I showed you at the start, what you end up with is something more like this, so a much more settled and compact ice reservoir. Now, because the ices are oxygen rich, what you end up doing is removing oxygen from the outer regions of the disk. So you end up pushing the gas phase elemental abundance of C/O around 1 or even higher. And that's where you start to get kind of hydrocarbons being formed and being abundant enough to kind of emit quite strongly in the disk. And this picture that we now have actually sits quite well with some interesting results from Herschel, which was the surprising lack of water, especially cold water, towards protoplanetary disks. So there was only 2 confirmed detections of cold water with Herschel, one of which was TW Hydra and another disk HD 100546 as well. And the fact that the cold water emission was weak or absent kind of sits nicely with this prediction that we're actually removing a lot of oxygen from the outer disk. So everything I've showed you so far, so there's a couple of nice examples of these molecular rings that are tracing different things. Those were all still at quite moderate spatial resolution. So what are we actually seeing at high resolution? So first of all, I just want to show you one of the science verification data sets from ALMA towards this disk here, which was 163296. And what you're looking at is emission from the CO molecule J = 3:2 transition. And you're looking at the emission from this transition as a function of space, so right ascension declination, but also as a function of velocity. So we're stepping through in velocity space. Now, if you take a protoplanetary disk, for which the gas is orbiting close to Keplerian, so it has a Keplerian rotation profile, you incline that to the line of sight, then you will have one side of the disk will be orbiting away from you and the other side of the disk will be orbiting towards you. So we expect this kind of what we actually call like a butterfly type velocity profile in what we call the channel maps as we're stepping through. And so we had hints of this in previous data with other interferometry data like Plateau de Bure and SMA, for example, but this was a really, really beautiful example of exactly that butterfly emission pattern as we step through in velocity space. So here we have the blue shifted emission, here we have the red shifted emission, and here's the emission at the source velocity in the center here. And that's because of these projected velocities. So these are what we call isovelocity contours here. So these data are really beautiful, but also they're really interesting because we can see the top side of the disk and we can see also the back side of the disk. So we can see the aspect ratio of the disk emitting surface. So that already gives us an empirical measurement of the vertical location of the CO emitting surface. And then the other thing that's really interesting here is that you can also directly see the freeze out of CO in the midplane. So you can see it here, you can see it here, you can see it here. So where the CO starts to disappear in the channel maps is showing you where the CO is beginning to freeze out. So by going to these much higher resolutions, you get a huge step up in information, if you like. You can start to actually empirically measure things like emitting surfaces and also measure directly from the data the location of, for example, the CO snow line in this case. So another thing that you can do is you can look for deviations also in that expected Keplerian profile. And this is a really nice result from kind of a now unique tool for trying to find the presence of embedded planets and protoplanetary disks. So this is work from Christoph Pinta, published just last year. This is a disk called 97048. And what you're looking at is one of these particular channel maps, so at a particular velocity. And you can see here the emission from the CO 3:2 transition. You can see the top surface and you can see the bottom surface. You can also see here the faint continuum emission just imaged in this single channel, so that's why it's quite faint. And then what you can see here in the circle is a little kind of perturbation or a velocity kink. So it doesn't look nice and ordered as we would expect from a Keplerian profile. You see this kind of little deviation or kink or wiggle. So you'll see lots of different terms for this in the literature. And this is really interesting. This is telling us there's something going on in that region of the disk that's perturbing the local kinematics of the gas away from Keplerian. And the other interesting thing about where this deviation is it's sitting in a dust gap. So you have two rings here. Here's the inner ring, here's the outer ring, and this deviation is located at a gap. And the explanation for this is that, or one of the explanations for this is that you have a planet in the midplane that is growing, so it's accreting from its environment. It's creating a torque that's then pushing out the gas, creating that gap that's then trapping the dust. And then what's creating the velocity deviation is that the planet's actually pulling material, not from just within the midplane, it's actually pulling material down from the disk surface via these meridional flows. So we have these flows in our atmosphere as well. So that's what's actually creating this measurable velocity perturbation in the location of that dust gap in that protoplanetary disk. So this is really interesting. So there have been a couple more tentative examples. That's a really nice clear-cut example. People are now looking for these deviations in existing data and new data as well. So we have these meridional flows, but also for people interested in planet formation, you can see here that this planet that's forming isn't accreting its material from its surroundings in the midplane. At this point in its evolution, it's accreting material from higher up in the disk surface. So no longer should we be thinking about just disk midplane composition as being important for planet formation. We need to start thinking about the disk as a whole as being important for planet formation. And this is already being explored that these gas giants, that they need to be gas giants to have these effects, that they're actually assembling their atmospheres from material in the disk surface that I've showed you could be carbon rich rather than from the disk midplane. So this is already starting to be explored by astrochemists that have skills in disk modeling. So kind of looking on at also what we see at these very high resolutions. So this is a really nice result, I think, that's kind of leading up to what I'm going to show you in our large program. So this is the result from the ALMA survey looking at younger sources. So this is really beautiful data at 0.1 arcsecond resolution. So to give you a physical scale, that's 10 AU at 100 parsecs. So really, really high resolution compared to what we had before. And this is towards DG tau B. And this is a really beautiful data set. You can see here in the CO emission, you can see the outflow cavity really nicely emanating from the star down here. Looking at the CO kinematics, you can see this kind of swirling disk of gas, molecular gas. It's also got these trails that seem to be from accreting filaments from the surrounding envelope. When they look at other molecular tracers like formaldehyde, CS and CN, I mean, they can see that these different molecules are tracing different environments within this forming star. So the H2CO, the formaldehyde, seems to be sitting within the disk. The CS seems to be more connected to these filaments and the envelope. And then the CN, which we tend to think of as being a photochemical tracer, seems to be coming from more around the surroundings. But you can see that in just these four molecules, you can trace a huge number of different components. The molecular emission from the disk, from the envelope, you can see evidence of infall in the kinematics, as well as the very powerful outflow that's coming from these objects. So maybe not unsurprising, when we go to very high resolution, we start to see a huge amount of detail. We don't see all of these emissions all mixed up together that we have to try to disentangle. We actually start to spatially resolve. Okay, so for the last few minutes, I just want to give you an overview of the chemistry of planet formation. So this is the name of our ALMA Large Program. We were awarded 130 hours in cycle 6. And we're just coming to the kind of the end of a long process of data imaging and analysis, and we're just about to submit the first papers from this large program. And the key idea behind this was that we really wanted to do high spectral resolution, so down to 0.1 kilometers per second, to exploit that information you can get kinematically. High spatial resolution, so again down to that 10 AU scale at 100 parsecs, and really high sensitivity. So 1 millijanskis per beam is really what you need at these high resolutions to start to pick up emission from, especially those larger molecules for which the emission is intrinsically more weak. So these were kind of our little cartoon of our different aims. So 130 hours of ALMA gives you a lot of information, gives you a lot of data, of course, but our motivation was looking at things like what are the distribution of organics and also the elemental ratios that we have, especially in the planet forming region, a region that traditionally we could not get to with previous facilities. We wanted to look at the relationship between these dust substructures that we very clearly see in the thermal emission and the chemistry, to try and get an understanding of how those two effects are coupled, or if they're coupled at all. We wanted to get a handle also on what's kind of going on in this outer disk. So for example, I showed you C2H and DM tau. So we see a different chemistry happening kind of beyond the pebble disk versus further in. And also we wanted to exploit high resolution to start to see empirically the vertical distribution of molecules in disks. So actually trying to measure the emitting surfaces empirically rather than relying on forward models in order to extract that information. So that's just a snapshot of some of the key science questions that we had. We had 5 sources, 4 spectral settings across band 3 and band 5, 20 molecular species, including a lot of isotopologues. We tried to get 2 or more transitions for 50% of species because we also wanted that excitation information as well. So here are 5 sources, sorry. So you've seen IM-Look was one of our sources because of its beautiful spiral arms that we saw in the thermal emission. We also chose 4 others, so GM Origai, AS209, HD163296, and MWC480. And for varying degrees, we knew all of these disks were molecule rich from previous observations. We wanted to be sure of our detections at these high sensitivities and spatial resolutions. And we also chose slightly different morphologies, so HD163296 with its very defined rings, AS209 with its kind of large gap that it has in the outer disk, and then GM Origai and MWC480 with the more shallow rings. So we tried to pick sources which we knew were molecule rich, but also had a wide diversity of substructure in the dust. So if we look at these protoplanetary disks at 0.1 arcsecond spatial resolution, I just want to give you an idea of what the leap up in resolution is. So what you see here is an emission line, HCN 3 to 2, and this is at 0.5 arcseconds resolution. You can see quite nice blob of emission in the middle here, and there's some fainter extended emission that we see at this resolution as well. Here's the beam down here. So whenever we add in our long baselines and we really get that beam down by a factor of 5, then this is actually what that emission looks like. You can see our beam here has gone down considerably. We're now at 0.1 arcsecond resolution. We have a central ring of emission. It's not a central blob of emission anymore. And we also have this fainter outer ring, as well as a hint of kind of extended emission in the outer disk as well. And because this is very high signal to noise data, we can actually put a stretch on this image, and I can show you the extent of that molecular disk way out up to a few hundred AU. And you can see various different features. You have the inner ring, this fainter ring. There's also a little gap here as well. And we can also very clearly see the edge of the molecular disk traced in HCN 3 to 2. So again, a huge amount of substructure compared to what we might have expected with previous generation observations. So here's another example here. This is the same molecule, HCN 3 to 2. This is CN 1 to 0. We think of CN as being a photochemical tracer, tracing the upper disk atmosphere, but actually this molecule is emitting from quite deep down, as we can kind of see in this image here. This is in the band 3 data, so it's slightly lower resolution than the band 6 data because it's at lower frequencies. If we take another molecule that we think is tracing the disk atmosphere, C2H, we can see that again, it seems to be coming, we don't see that kind of aspect ratio that you might expect if it was coming from high up, like in the scattered light. It does seem to be coming from quite deep down, but you can see that again, the C2H is not in a blob. It's in these quite defined rings, and the rings of emission are different to the rings of emission in HCN. And again, if we put a stretch on, because we've got high signal to noise, you can see that the C2H emission is very defined. There's not very much in the extended outer disk, which is different to HCN. So these two molecules are doing something very different, but have some similarities in these ring structures in the inner disk. So here's kind of a snapshot of all of the results that we have so far, at least in the band 6 line. So here's our 5 sources that you see on the y-axis, and then along the top you have the different molecular tracers that we targeted in band 6. I've already shown you the C2H and the HCN in 16V296, and you can see that no two disks look the same, so very much to what we're finding from the continuum surveys at similar resolutions. No two molecules seem to have exactly the same morphology. There's some overlap, so for example here DCN and HCN and AS209 seem to overlap a little bit. But again, what the disks themselves are doing in each molecular line is actually quite different as well. So there's this huge diversity of substructure. Might not be surprising because we put another layer of complexity. And we also have really no consistent correlation with dust structures. Each molecule in each disk has a different behavior. And this is something that we now have to try to understand, and I think something that the modelers now need to kind of take forward. So I'm a little wary of time, so I could just skip to the end and just, I don't want to take up too much more of your time. Let me just, I think you should be able to see this final slide. So I did have another little section, but I'm a bit wary of time and I would need a little bit longer than a few minutes. But I think I gave you a pretty good overview of what we've been doing and how far we've come. So just to summarize, in disks with ALMA, we're starting to resolve snowline positions. So we're really starting to put our solar system in context with where its snowline positions were relative to in disks in other planet-forming environments. I didn't show you this, but we can now actually use that excitation information, also the radially resolved emission, to start to actually empirically derive 2D distributions of molecular structure in protoplanetary disks as well. We're starting to reveal these new organic reservoirs, so we're starting to see emission from these larger molecules at much higher resolution as well. And we're seeing these organic molecules, especially complex organic molecules, and in particular we're seeing that the cyanides in particular are quite abundant. And for those of you interested in more the prebiotic chemistry, cyanides actually play a critical role in some of those mechanisms. And we're also starting at these high resolutions to start to image molecules and the molecular composition in the planet-forming regions. So we've done a huge step forward just in the past 10 years by exploiting rotational observations of rotational emission lines from ALMA, and now also showing what the power of high resolution can do. And I think I'll finish there just on the R, and happy to take any questions.
Many thanks for this really comprehensive talk, Catherine. Now it's time for questions, as you said, and I would then like for people to ask questions. Either you switch on your video that I can see that you are going to ask a question, or okay. So please, could people then who wanted to ask questions maybe switch the video on so that I can see that you want to ask a question. Otherwise, alternatively, as said, you can actually put it into the chat. So here, Louis, you have got a question. Please go ahead.
Yeah, I have a question. I would like to ask, what is your, I would say, your feeling about trying to connect the observed molecule in the gas phase with actually the solid phase observed in what we call the meteorites, or you may say asteroids, for example, now. But because actually for prebiotic chemistry, you need these molecules to find the Earth safely. And if they are not buried in kind of meteorite, it's not really going to work if it's only gas phase.
Yeah, that's a good point. I think that is still something that's still tricky to do. We do have a huge wealth of information in the solar system, of course. That's a point of truth, if you like. We know the outcome of planet formation and the role that kind of meteoritic impacts and asteroid impacts played in delivering that organic material to the surface of the Earth. So there's still, there is still a bit of I don't want to use the word gap, but I think that there's one thing that the data are telling us, and that's what the gas is doing. And then there's something that we need to do to then connect that to what the solids are doing. And it's hard to do that empirically. We can kind of indirectly probe the ice reservoir, because we know that certain molecules can't exist in the gas phase at high abundances unless surface chemistry is involved and is active. But then the step between taking those volatiles into the more refractory organics, that's something that we still need to work on, I think. And that's not just working on the chemistry. I think that takes like detailed modeling of the kind of the whole environment. So how do you take this cold material and process it into this more refractory organic material that then gets delivered hopefully to planetary surfaces? So it's really difficult to do it empirically just from the data alone, but certainly I think that modeling, future modeling, can help hopefully fill in some of that gap.
Okay, thank you.
Okay, then Flores has a question, I think.
Hi, Catherine. Thanks. That was a really nice talk. It's wonderful to see that all these predictions of physical processes in disks, like the settling and the radial drift, we can now really see that it's actually happening. And also, of course, the freeze out and the desorption, like the snow lines, that's a reality, not just a theory. I was curious, one further prediction of disk theory is the viscous spreading with time. Is ALMA or other facilities also giving us insight on how real that is?
That's a good question. We do have one paper as part of this first release, which tries to empirically, it's led by Coco Zhang, empirically derive the CO column densities radially through each of the disks using all of the isotopologues and all of the excitation lines that we have, different excitation lines that we have. And one of the interesting outcomes from Coco's analysis is that the surface density profiles that she derives do fit well, actually, with those predicted by the viscous evolution models, which is quite for the gas, obviously. So it does seem you still need to do a bit of. We're trying to do things as empirically as possible, of course, by not doing any forward modeling, but certainly through, you will see in that paper that just through trying to empirically extract those column densities, getting the surface density, they do look more like, for example, the predictions from the viscous spreading models than others. So that is potentially a little bit of evidence that these disks are in that act of spreading. Yeah.
Great, thanks. I'll have a look at Coco's paper then.
Yeah, we're submitting in the next few weeks, so hopefully won't be too long after that. We're kind of trying to get everything done in one shot.
There's a question for the talk from the chat from Isaskun Jimenez Serra. You see holes in most of the disks observed with the ALMA Large program. Are these holes real, or are they produced by large dust opacities?
That's a really good question. In some cases, it is, and in some cases, it isn't. What we are finding is that the emission is coming from much deeper down in the disk than we would have predicted. So again, like I kind of showed you the CN and the C2H, we might expect to be these photochemical tracers. We know these disks are flared, but actually even those molecules are sitting quite deep in the disk. And that does mean that in the very inner regions, if the molecular layer overlaps with the kind of the dust emitting surface, then yes, you can get affected by dust opacity in there. So for some of the CO lines, it's not affected by dust opacity because their emitting layers we can show are much higher up in the disk than where the millimeter dust is coming from. But for some of the other molecular tracers, then yeah, we do have that issue. So yeah, it's it depends on the molecule and it depends on where its emitting height is relative to the dust emitting height.
Okay, there is another one on the chat, which is by Anton Vasyunin. And the question is, does the existing knowledge of binding energies, is the existing knowledge of binding energies sufficient to interpret observations of snow lines, or is there room for improvement?
That's a good question. Thank you, Anton. I think at the moment, the CO snow line is the one that we can, I would say, best get to with the data that we have currently, or the resolution that we have currently. And CO thermal desorption has been very well studied for, I think, quite a while now. I know that there are some spread perhaps in the value because of the different ice environments, or the way that perhaps some of the lab experiments have been done, whether that's done wavelength dependent or done with a broadband lamp. But I think that the error, if you like, or the spread in those values is probably a lot less than the spread in the value of the error bar we have on the temperature structure of the disk. So even though there's a little spread in the values, for example, the CO desorption temperature, that still gives us very, very good constraints on the physical scales of the disk, if you like. For other species, I know that, for example, cyanides, right? So we're finding these are quite abundant. Methyl cyanide, cyanoacetylene, for example, are very bright, very compact emission. And as far as I know, there's not much data out there on those molecules, for good reason, because they're poisonous, and who wants to work with horrible toxic materials? So certainly those molecules, I would say that they're much more uncertain, and kind of one of the things that we need to do is to try to see if we can actually see in the data where those snow lines might be. But yeah, I think for molecules like CO, the data are really good quality and much better than our models, so they're brilliant. But we are lacking perhaps data for the more say poisonous molecules. Poisonous in the lab, but still important, I suppose, in astrochemistry.
Okay. Anybody else wanting to ask a question? Yes. Alex Roof, please.
I can't hear you, Alex. I can see you talking. I'm also happy if anybody wants to talk offline about anything or send me an email, please do. I'm very happy to chat to anybody about anything that we've done.
Yes, I want also to make an announcement in the meantime. In 2 weeks, on the 23rd, we will have another seminar again. And this time it will be by David Donaire from the University of London, Sweden, who will be talking about philosophical and historical issues in astrobiology. So you will hear something a little bit more different. So I can't see yet any text from you, unfortunately.
So Alex, if you email me, I'm very happy to answer your question offline. Just send me an email.
Okay, now we have got it. My question is related to really complex organic molecules. Is it that large complex organic molecules might be trapped in the dust, for instance, or is it a problem of detection and we can expect them to see with JWST?
Okay, that's two questions. So the first one, so in terms of what we can detect at millimeter, submillimeter wavelengths, we're constrained by two things. First of all, is that these large complex molecules are sticky, like you say, and they do prefer to be in the ice at low temperatures or in the dust than in the gas. So the abundance of them is very, very low. And also, even with the power of rotational spectroscopy, the more complex the molecule, the larger the number of excitation levels and excitation lines. So you're kind of spreading that already quite low abundant molecule over many more energy levels, which makes the emission from individual lines significantly weaker. So we do have a detection issue there. So in terms of what we can do with JWST, it's going to be hard to see complex molecules in the infrared, because at some point, it depends on the quality of the data, and if there's spectroscopists in the audience would be better posed to answer this question than me. But at some point, it's hard to then detect. So you start to then detect more functional modes and functional groups rather than individual molecules in the infrared. So you might see a signature from, say, a methyl group or an ethyl group, but it might be difficult to know what's hosting that functional group. So in the infrared, it can be challenging uniquely identifying absorption or emission features. But again, there's probably someone in the audience who's more of an expert on that. Yeah.
Yeah. Okay. Any other further questions? If not, let's thank Catherine again